Played with the volume, so as soon as you start the line down, just it might be too loud. Should be.
It's easier to make it softer than it is louder because it's a YouTube video, so I can just pull it back.
The system is not maxed out. The YouTube is really maxed out the system. Or the YouTube dongle.
Okay, before I present the speaking today, tomorrow there is a special seminar by Neta Bar-Cohen, and she's going to talk about the formation and uplift of the standard sea range in California. Okay, so just a reminder for that. Today our speaker is Bronwyn Dixon. She did her undergrad and master at ANU. Her PhD was at Melbourne University, and now she's doing a postdoc in the UK, in the University of Reading. She's going to talk about the Australian public-private record.
Thank you, Yakov. Good morning. My name is Bronwyn. Thank you very much for inviting me to be here today. As Yakov said, today I'm going to be presenting just a small portion of my PhD work that focuses on reconstructing Australian climate during the past 2,000 years using a diversity of natural archives. I'd like to take just a moment to thank my co-authors, two of which are also my PhD supervisors, without whom this work would not be possible. So during this talk, I'm going to give a quick introduction about recent climate change on the Australian continent, and then go into a bit more detail about what drives climate variability in this region of the world. How do we actually extend our knowledge of climate drivers back through time? Why should we focus on just the past 2,000 years, the Common Era? And then we'll get into the more interesting stuff. What is the state of our paleoclimate record at the moment? And given what we know about the state of the records, how can we actually work to start to synthesize these records in order to gain a more detailed understanding of how the climate has changed and what actually drives this variability through time? And then I'll sum everything back up and then talk about some of the exciting possibilities for how I can extend this work into the future. So just because of its sheer size, the Australian continent is a land of extremes, where it extends across numerous lines of latitude. In the northern section, you have the monsoon region, where you have very strong seasonality in the rainfall. You have the arid center, so the very familiar scenes of the Australian outback. And then along the coastal fringe, you have a combination of tropical rainforest, temperate rainforest, and temperate woodlands. And like most places in the world, we've seen dramatic changes in the climate conditions over recent decades. So on the screen at the moment, we have the trend in temperature over the past 30 years and the trend in rainfall over the past 30 years. So despite the fact that it's a diverse continent, we see an incredible degree of consistency in temperature change since 1970. But it's a very different story when we're looking at rainfall, where we see a very strong discrepancy between the east and the west side of the continent. That on the western side of the continent, we actually see an increase in rainfall since 1970. And then on the eastern side of the country, we see a decrease in rainfall since 1970. And the hydroclimate is particularly important because within Australia, it's a small population, but most of the population is gathered near the coastal fringe. So the major cities are Brisbane, Sydney, Melbourne, Adelaide, and Perth. And then additionally, we have a very strong agricultural tradition, and the main agricultural area is in New South Wales, Victoria, so the southeast part of the country. Now, as soon as I highlight where the population centers are and the agricultural centers are, we see that these are located in the area that has a very pronounced decrease in rainfall. That's why we're concerned about, or that's why we're wanting to know what the natural range of variability in rainfall is, how has it changed through time, and how can we use climate drivers and drivers of natural variability in order to predict what may happen into the future, sort of putting this information into the models. So these are the general trends that we've seen in recent decades, and then superimposed on top of that, we see an increase in the extremes. So between 1997 and about 2010, we had the Millennium Drought, where that was the worst drought recorded on the instrumental record. That drought broke in 2011, 2013 with two very extreme La Nina events, and we ended up seeing flooding. This is a picture of Brisbane, so again, one of the major cities. And then in addition to that, we've also seen an increase in the number and the severity of heat waves. And also, I don't know if it made it into the news here, but this year has been the worst year on record for the bushfire season. So Queensland bushfires especially, the season is starting earlier, the season is more intense, the range of the geographic area where we have bushfires is increasing, and then of course this puts a strain on financial resources, human resources, etc. So for the reasons highlighted here, understanding what actually drives climate within Australia is an important and an interesting topic of study. So what do we know drives climate variability within Australia? So again, like I said, it's a huge continent, huge space. So there's two primary things that drive variability. One is the hemispheric-atmospheric circulation patterns. So within the southern hemisphere, the most important features are the intertropical convergence zone, so the climatological equator, and that shifts north and south through the year and brings the monsoon rains to northern Australia. And then that constitutes the upward arm of the Hadley cell, and then the downward arm of the Hadley cell leads to the subtropical ridge, which is a band of high pressure that normally sits directly in the middle of the continent. And then below, or to the south of the subtropical ridge, then we have the westerly wind belt. And this is responsible for bringing frontal rainfall up from the Southern Ocean into southern Australia. So in addition to atmospheric circulation, Australia is uniquely positioned at the intersection of three ocean basins. So the climate and the climate conditions are influenced by the Indian Ocean, the Pacific Ocean, and the Southern Ocean. And each of these oceans have their own coupled ocean atmospheric climate modes. And these three climate modes, so in the Pacific Ocean, it's El Nino Southern Oscillation. In the Indian Ocean, we have the Indian Ocean Dipole. And then in the Southern Ocean, it's primarily an atmospheric mode, and it's the Southern Annular mode. So I'm just going to give a very quick introduction about how these climate modes actually influence Australian climate, using my favorite piece of science communication. And also you may hear that I don't have a very strong Australian accent because I was born in the US. So I'm going to allow somebody with a much nicer and a much stronger accent.
This is Enzo, Indy, Ridgie and Sam. They represent 4 climate processes that affect our rainfall variability across Victoria. These 4 sheepdogs love rounding up our rainfall. From a farmer's perspective, when they're behaving, they bring moisture from the oceans and allow it to fall over Victoria as rain, hopefully delivering the right amount at the right time. But they don't always work the way we'd like them to, and can sometimes scatter the mob, effectively chasing rainfall away from Victoria. Over recent decades, some of these dogs have changed their behaviour, contributing to our extended dry spell and the changing weather patterns that many farmers have noticed. While we can't control what these dogs are up to, the Bureau of Meteorology and the Victorian Department of Primary Industries have new and valuable tools that can assist farmers in keeping track of these climate dogs, helping to predict the likelihood of rain over the coming season and manage climate risk. The El Nino Southern Oscillation, or ENSO, has a big influence on Victoria's climate over winter and spring. The Pacific Ocean trade winds blow from an easterly direction, pushing moist air towards Australia. This moist tropical air is a big source of rain across eastern Australia, including Victoria. But ENSO's behaviour can vary from year to year. During La Nina, ENSO chases greater amounts of moist tropical air across Australia. Many La Nina years have seen higher rainfall in Victoria during winter and spring. During El Nino, ENSO changes his mind and drives warm, moist air towards South America instead. El Nino years have often resulted in drier winter and spring periods for Victoria. Each year, climatologists follow ENSO's behaviour, providing us with a potential rainfall outlook for Victoria. So ENSO is definitely an important dog to keep an eye on. This is the Indian Ocean Dipole, also known as Indy. He influences Victoria's rainfall in winter and spring. Indy brings rain to Victoria when the northeastern Indian Ocean increases the amount of moisture it provides to the atmosphere. This moist air is herded across Australia and can deliver significant rainfall into Victoria. When the northeastern Indian Ocean produces less atmospheric moisture, Indy doesn't drive as much rain towards Victoria, and we can end up with a drier winter and spring. Historically, Indy has been a significant source of rain. However, in recent years, Indy has not been chasing moisture down south as often as farmers would like, reducing the average rainfall for Victoria. Indy is closely watched by scientists who make limited predictions on his behaviour before winter and spring arrive. Keeping an eye on Indy's behaviour can provide an indication of the expected rainfall coming from the northwest to Victoria. This is ridgy, or as scientists like to call him, the subtropical ridge. Ridge is one of the 4 major drivers that shapes Victoria's seasonal weather. So let's look at how he does it. As warm air in the tropics continually rises, moves south, then cools and falls, large areas of high pressure are created. These high pressures, in this case ridgy, are great at blocking rain-bearing fronts. From November to April, ridgy chases away cold fronts around southern Australia for days or even weeks at a time. Occasionally, cold fronts sneak through, and if they connect with moist air from the tropics, Victoria gets some summer rain. As winter sets in, ridgy heads north, and the cold fronts find it much easier to reach Victoria and deliver their rain, until ridgy returns next November. Ridgy does this every year, but in recent decades, he's been getting more effective at chasing away cold fronts from Victoria, explaining a lot about drier weather. The Bureau of Meteorology has observed that ridgy's increasing strength is related to the rising global average temperature, but the scientists are continuing to investigate how this climate dog might change his behaviour in the future. Meet Sam. Sam herds cold fronts up from the Southern Ocean, a significant source of rain for southern Victoria. If we take a look at the Southern Ocean, we can see westerly winds circling around Antarctica, throwing out cold fronts of stormy wet weather. The strength and position of these winds is known as the Southern Annular Mode, or SAM. Sam is an unreliable climate dog, often changing his behaviour in a matter of weeks, which can affect Victoria's rainfall. When Sam is tied up, strong winds are pulled in towards Antarctica, and there is a reduction in the number and strength of cold fronts that reach southern Australia. When Sam is let off the leash, the westerly winds move further north, increasing the chance of frontal activity and potential rainfall. Over recent decades, Sam has found himself tied up more often, resulting in less cold fronts and rainfall for some parts of Victoria. Sam's behaviour is complicated, so scientists are in full swing to try to understand how this climate dog might impact on Victoria's weather down the track. This is Eastie, better known as the East Coast Low.
Those are all the important ones. So, it's my favorite bit of science communication, even if their view of what a scientist looks like might not be entirely accurate. Full screen. Okay. So now that we know what some of the possible influences are, the main limitation in Australia is that we're a very young country. Our instrumental records only go back approximately 100 years maximum, but for most places outside of the East Coast cities, you might get 50 years of instrumental observations. So that's where the geology side of things comes in. So the way that we extend our knowledge back through time is using paleoclimate proxies. So as many of you are familiar, these are natural archives that their characteristics are influenced by the climate and environmental conditions at the time of their deposition. So the most common archives are ice cores, tree rings, corals. I'm not sure how common the pack rat middens are. Maybe USGS and I disagree on that. Sediment cores and our beloved speleothems. And within these archives, the measured variables fall within 3 approximate categories. So we have our biological proxies such as foraminifera, pollen, diatoms, etc. our physical proxies, so magnetic susceptibility, grain size measurement, etc. And then chemical proxies, presence and absence of chemical elements, changes in concentration through time, and isotopic changes through time. And then using these paleoclimate archives, what we're wanting to do in this case is create a robust baseline so that we can understand what the natural range of variability may have been. And my work focuses on the past 2,000 years, known as the Common Era. And this is a strategic period of time for a few reasons. First of all, the boundary conditions of the climate system are fairly well constrained during this time. We know what the Milankovitch parameters have been. We have records and reconstructions of sea level rise. We have records and reconstruction of solar variability. We have records and reconstructions of volcanic activity. Also within this time, we have recognized warm and cool anomalies. So we have the Little Ice Age, we have the medieval climate anomaly, even though the timing and intensity of these events vary across the globe. At least we know that these are things that we can look out for. And then the final reason why we like to focus on the past 2,000 years is that it has the best data coverage. So the figures that we have on the screen reflect, there's a working group sponsored by Pages, the Pages 2K network. This is a figure from, I think it's a 2013 paper, so this is only annually resolved paleoclimate records, but you can see there's fair spatial coverage across the globe, including Australia. And then as you move towards the present day, the number of available records increases. So now that we know when we want to study and what we're going to do in order to reconstruct the climate during this time, now we shift our attention towards the Australian perspective. So there's been previous work to look at the status of the annually resolved paleoclimate records within the Australasian region. These include tree ring records and coral records primarily, as well as the ice core records. But my work focuses on the non-annually resolved records. So these can include lake and wetland sediment cores, marine sediments, peat cores pulled out of our peat bogs. Speleothems can be annually resolved, or they can be sampled at a lower resolution. So that's one archive that spans both of these categories. And then also looking at the geomorphic features. So the dune fields, the shoreline dates within the arid center, etc. And there's been work to identify the current state of the annually resolved records, but so far there has not been any work to examine what the low resolution records are like. That's where my work comes in. So first step, our favorite literature review, and trolling through the literature, I identified 675 records that are already published or exist within PhD and master's theses. And then what we're wanting to do is, given that we're wanting to focus in on the past 2,000 years, we wanted to apply a selection of, or a group of selection criteria in order to identify the highest quality records within this time period. So our selection criteria that were actually established by the Pages 2K working group was that there has to be a relationship between the measured variables and climate, because we're wanting to reconstruct climate. The records need to be at least 500 years in length, so 500 years out of the past 2,000 years. There needs to be an age model with at least 2 or 3 dates. I would have a hearty conversation with them about that particular selection criteria, but that's a rant for another day. Average sample resolution between 2 and 50 years. This is because we're wanting to look at interdecadal or decadal to multi-decadal variability during this time. And then, again, logic. The records need to fall within the Australasian region so that we can actually focus in on what's being recorded within this zone rather than inferring teleconnections through time. So when we applied these selection criteria to the 675 records, 22 passed the test. So even though, again, this is a huge geographic area, we have a long way to go in terms of geographic coverage of paleoclimate records. The ones that did pass the test, these 22 records, you can see that they fall within two very distinct groups. So there's one concentration within the maritime continent. This is a combination of marine cores and lake sediment and speleothems within that region. And then the second group that you see is within Southeast Australia, and that's only lake records. And then there's also this, the one New Zealand record here, and even though it's in New Zealand, it's actually a record of Australian dust that's been transported over the Tasman Sea. So even though it's located within Australia, we assume that it's a record of, or it's located within New Zealand, we assume it's a record of Australian climate variability. So just for a pilot study, I focused in on the records that are located within Southeast Australia. And now that we know what data is actually available to examine this time period, there we go, Southeast Australia. So most of the records are located, there's one marine core, and the rest are lake cores located fairly close to the coast. And then we also have one peat bog that dust accumulation through time has been measured. So it's 8 records total. And so it's an interesting experiment. If you only have 8 records, how do you start to bring these together? They have a diversity of archives, they have a diversity of measured variables, they all have different resolutions, they all respond in their own way to climate variability. How do we find the consistencies within all of this uncertainty? So going back. For each of these sites, this is Lake Keelambeet, probably one of the best studied locations within southern Australia. As we can see, as is very common, it's a sediment core and there's multiple variables that have been measured. So we have grain size changes through time. This is present going back through the Holocene. Grain size variability, we have lamina count, we have ostracod measurements, we have the geochemistry from the ostracods, and we have a salinity reconstruction based on the ostracod diversity. So multiple variables measured within the sediment core, so we know how things have changed through time. And then the other question, or for each of these sites, one of the fundamental questions is, when did these changes occur? So this is one of my favorite things to really focus in on is, I love creating age models. Call me a nerd, but. So for each of these sites, I created new age models just so we can start to incorporate the uncertainty of the records themselves. So I created new age models in a program called Bacon, which is run through R. It's a Bayesian program. So what it does is it actually runs at least 10,000 possible age depth relationships, and then uses this cloud of possible relationships to infer what the most likely age depth relationship may be. So each of the, that's a bit faint on the screen, but we have a combination of radiocarbon dates and OSL dates on the sediment core. And then in this case, it's a very well-behaved site, so we have pretty much a linear relationship between, this is depth from the surface along this axis, and then we have the opposite direction for the calendar years along the bottom. So from present back through the Holocene. So we have a new age model for each of these 8 sites. We have a collection of variables for each of these 8 sites. And then the first step in trying to bring this together is, the technique that I've used is a 2-tier approach. So what we're wanting to do is we're wanting to perform data reduction at the site level so that we have consistent signals coming from the variables at each site. And then the second step is to bring these signals from the individual sites together in the regional perspective. So for each of the 8 sites, if they had multiple variables measured, then I performed either principal component analysis or DCA. And those are the sites that you see red and blue. Those are the top, the first 2 data reduction outcomes, so the first 2 EOFs. And then there's also some sites that only have 1 measured variable, or 1 variable that is assumed to be driven by hydroclimate change. And then these are the sites that you see with the green lines. And you can see that there's a cloud instead of just a single line for each of these sites. One of the things that I was wanting to do within this research was to transfer the uncertainty that we measured within those Bayesian age models and transfer that across to the time series of the variable of the measured proxies. So even though this is changes in proxies through time, so if we look at the snowy mountains, this is dust accumulation. You see that there's the envelope, and that just indicates we have the measured values, but there's uncertainty as to when that measured value was actually deposited. So we have the time uncertainty incorporated into all of our time series for our paleoclimate records. So now that we have sort of the concentrated or the concentrated signals from each of these sites, then the next step is to bring all of these time series together into a regional principal component analysis. So it's 22 time series from the 8 sites. And when we bring all of those together, principal component analysis is simply finding the independent consistencies within all of those time series. So again, you see that there's envelopes of uncertainty, and that is derived from those Bayesian age models. So yes, we combine the distilled data from the multi-proxy sites, and this is reflecting patterns of change that are reflected across Southeast Australia. And what we see across Southeast Australia, these 2 EOFs, so patterns of change, have been oriented so that they reflect the published interpretation of the paleoclimate records. And these indicate that there's been a steady increase in effective moisture across Southeast Australia between 850 Common Era through to 1750 Common Era. And then an independent from that, we have another mode of variability, and that's much more, you have peaks and troughs in this. So this is also assumed to reflect rainfall change, hydroclimate change, but in addition to the steady increase in effective moisture, we see periods of slightly higher, slightly lower, slightly higher, etc. Together, these 2 modes of variability, these 2 EOFs, reflect 48% of the variance, so nearly half of the variability in across those 8 sites, across multiple measured variables. We can explain about half of what's going on, which is actually pretty good for this kind of work. We see overall wetting.
But what's the energy of the first and the second mode? What's the duration?
Not energy, it's variance.
Variance.
48%. 50% together.
No, together, no. That's the first and the second.
I have charts afterwards, so I'll be able to show you at the end of the talk. So then the next step is actually using the published interpretations of the individual records in order to try and figure out, we know that these are modes of hydroclimate change, but what exactly is going on? What's driving that hydroclimate change? So when we look at EOF1, so the one here in red, and we go back to the original papers, even though the specific interpretation of the variables varies site by site, the consistent thing that the original authors, the independent authors, all said was, we think that the westerly wind belt is controlling the pattern that we see. So we'll test that in just a moment. And then we look at the second mode of variability, so EOF2. And what we the agreement that we see is that it actually agrees very well with the ice core records, which are interpreted to, or that actually agree quite well with independent rainfall reconstructions in Australia. So that's more of a hemispheric connection. And again, that's something that...
Australian.
Pardon?
Which ice core?
If you go directly south, we still claim it. It's still within our region. It's the Law Dome record. So this is possible reflection of a larger picture mode of variability. So, I hope everyone can see. We love our wiggly lines in paleoclimate. So one of the things that I was wanting to do with interpreting this is to see what the degree of agreement is between the low resolution records and high resolution records. So as one of the previous figures show, we have a much higher number of annually resolved records in Australia, but in general, the duration of those records is much shorter, and there's arguments that the preparation of annually resolved records generally has a much higher degree of smoothing, so you're more likely to lose some of the lower frequency variability when you're trying to piece together composite records from tree rings or corals. So that's the secondary thing that I wanted to test, is what is the agreement between the low resolution and the high resolution records. So again, these are interpreted in terms of hydroclimate variability, but there is a degree of connection between hydroclimate and temperature. So the first thing that I wanted to look at was, is there agreement between the temperature reconstructions and the hydroclimate reconstructions? So the first two sets of lines that you see in this huge figure, the green one, so here, is a composite tree ring record from Mount Reid in Tasmania that I have highlighted on the map here. And this is from one particular stand of trees. And even though there's approximate agreement that you have a bit of a peak in the first millennium, there's not that, I don't have the figures with me now, or I don't have the exact numbers now, but there's low degree of agreement between the Mount Reid temperature record and my low resolution reconstruction. However, there's a newly published temperature record that's created from a composite or multiple paleoclimate records, multiple archives, so tree rings, corals, ice cores, and there's a much higher degree of agreement between periods of lower effective moisture and higher temperature, and higher effective moisture and lower temperature. So that was a secondary finding, is that these composite records actually show better agreement, or higher agreement with both the low resolution and the high resolution. So most likely the temperature does have an influence on what's going on. And what we're wanting to do but the temperature record is showing that there's a decrease in temperature up until approximately 1800. So the period that's covered by this low resolution reconstruction, we see a decrease in temperature. And then we see the increase in effective moisture, or increase in rainfall during that time. And also that's not shown on this chart is there's a concurrent decrease in sea surface temperatures during this time. So land temperatures are decreasing, sea surface temperatures are decreasing. How does that drive our changes in rainfall? Does it drive our changes in rainfall? And there's two possibilities. One possibility is that a decrease in temperature is actually going to limit the amount of moisture that can be transported from the ocean to the land surface. And that would have the opposite signal from what we see here, but it could possibly explain some of these higher frequency wiggles. Or another possibility is that evaporation is decreasing. So if you have decreased evaporation, then the effective moisture is going to increase because it's actually staying within the soil, it's actually available for recharging lakes, it's available for increased vegetation, etc. So what I was able to do was there's a hydroclimate reconstruction, again, based on annually resolved records. And you can see that it's much shorter. This is from Southeast Australia, and this is from East Australia. And there's... Oh, I'll come to questions at the end of it. So
just what are the parameters that are shown here? It will not do us any good explaining without telling us what are the parameters.
This is rainfall reconstruction in millimeters.
Okay, that's useful to know.
Yeah. So this is in Southeast Australia, and this is in East Australia. And the green is winter, and the orange is summer. And what we're actually seeing within this figure is that there's a steady amount of, or there's no major change in summer moisture in the past millennium within southern Australia, but there is a decrease, or there's higher winter rainfall here during the Little Ice Age, which is highlighted in the gray box. So between approximately 600 and 300 years before present, we see that there's increased winter rainfall, which corresponds with higher effective moisture in the low resolution reconstruction. And so this is suggesting that the effective moisture that we're seeing here, or the increase in effective moisture that we're seeing here, is most likely driven by an increase in winter rainfall and a decrease in evaporation. So it's actually staying within the land surface. And then tying this back into the climate drivers, I was wanting to see if there's any possible influence of southern annular mode and the El Niño Southern Oscillation. And one of the most dramatic agreements is that there's a shift from positive SAM to negative SAM. So positive SAM is when most of the westerly wind belt is kept towards Antarctica. And then negative SAM is when the Antarctic winds expand up towards southern Australia, which delivers frontal rainfall to the southern part of the country. And we see a very dramatic shift at approximately 1400 CE from positive values to negative values. And this corresponds with a major shift in regional MCEOF number 2. And from that we infer that there's most likely that the higher frequency variability seen in regional pattern number 2 can be driven by the southern annular mode. And then also not shown on this graph is that there's an inferred shift in the ENSO system, so El Niño Southern Oscillation System. At approximately 1300 CE, there's a shift towards a more El Niño-oriented mean state in the Pacific, which would decrease winter rainfall at that time, which then agrees with some of the steady decrease that we see here. So overall, when we're bringing all of this together, we're seeing that the interaction between the southern annular mode and ENSO, so the interaction between the Southern Ocean and the Pacific Ocean, is most likely driving these higher frequency. It's still low frequency, but it's one of the regional patterns seen across southern Australia. So overall, we have a steady increase in effective moisture during the past 2,000 years. And then superimposed on top of that pattern, and is this interplay between two of the three ocean basins that surround the continent. So more negative SAM means that these frontal systems driven by low pressure belts can actually go further into southern Australia and deliver more rainfall. So overall, we've seen that even though Australia is a very large continent, we have a very small number of high-quality paleoclimate records that are suited for examining the past 2,000 years. However, even though we don't have a very large number, we can still use these records to start to understand what are some of the characteristics and what are some of the possible drivers that are actually influencing the patterns that we do see. Within Southeast Australia, we've identified a wet, cool little ice age. So again, like I said in the introduction, we've seen the little ice age in most places in the globe, but the timing and the intensity varies. So now we have the Australian perspective to add to that global story. And then within that time, we've seen that the seasonality of rainfall, so the fact that it's mostly winter rainfall, and with the positive feedbacks with the temperature, then leads to greater effective moisture. And then one of the most effective ways to interpret these low resolution records is to actually bring them together with the high resolution records. And then into the future, as we increase the number of paleoclimate records within Australia, we can use this relationship in order to extend our understanding further back in time. So once we get out of the range of tree ring records and coral records and speleothem records, then we can still look further back in time and extend that baseline period, which then increases our understanding of what may happen into the future. So overall, one of the main things is within Australian research, there's been a very strong divide in the past between the hydroclimate group and the temperature group. And the main thing for this research is that it demonstrates that you have to use these two climate variables together, and there's correlation, there's interplay between them. How does increases in rainfall affect temperature and vice versa? So into the future, trying to encourage these two separate groups to interact more and talk to each other, and then we can get a more holistic picture about what the climate variability is like, and then we can use that. The main application, in my opinion, is trying to tie this back into agriculture. That we've seen that our primary food production region is the same as the data coverage in this study. We can start to see how the degree of changes within the rainfall and how is this information, how can we apply it to how can we give it to farmers? How can we communicate it to farmers? And I think it goes to show with the climate dog animation, that was created for farmers. So we're starting to have more of a conversation, talk about how do we prepare for possible decreases in rainfall through time? How do we work together? How do we bridge that gap between the scientists and our food producers in order to work together to ensure that food security is as strong as possible into the future? Thank you very much for your attention. I'm more than happy to take questions if you have them.
Thank you very much. Questions?
So, back to my question. What is the relative strength of the first two EOF? One question. And then I may have missed you, but did you relate the first EOF to one of these basic mechanisms?
Indices. Like today. What are the EOF of today to try to see which one?
I haven't actually run PCA on any of the modern data sets, but that's a really good point because the data coverage here, given that we're using paleoclimate records, I looked at the time period that was covered by all of the records, which is why it cuts off at 1750 CE. So the next step would, there's probably studies, and if not, it would be future research topic. There's probably studies that run PCA on some of the annually resolved records, which would bridge that gap between these records and the instrumental period.
And it doesn't have to do with the single physical process, which is a combination.
So the first one's mostly temperature and the influence of temperature on evaporation.
So out of the many records, I guess it didn't show, I'm assuming there was some that showed opposite patterns. Is that the case?
There's always, so this is the loading. So this is the agreement between all of the individual data sets and the regional reconstruction. And there's one site in particular that it just didn't agree very well with all of the others. And going back to the original publication, there's a possible groundwater influence in that particular lake. So when rainfall decreases, that's when the groundwater influence increases. So then it can have the opposite signal to what we see in the non-groundwater influenced lakes.
Does it tend to be Lake Surprise?
Yes, one of them is Lake Surprise. You never know what you're going to find.
Okay, thank you very much. Thank you very much.
Thank you. I appreciate your help in organizing everything. I know it was a bit of a crazy couple of months.
How long do you need to stay there?
Until New Year's Day. So we're doing a bit of a geology tour around the country. We went out to Surrey yesterday, so that was very good.
So good to have you here.
Hello!
How are you?
Fancy seeing you here.
Yes.
How is your postdoc going?
Very good. If you have time, you should come by and look at the lab and what we do.
Yes.
Brilliant work. You take it to the next level, right? You take observations.
My non-speleothem work, I had to throw a few statistics in there as well into my PhD work, just to keep things fun and interesting, because Russell doesn't do stats. Russell Drysdale doesn't do statistics on his work. So I had my speleothem record creation and then all of this synthesis work to be able to balance that out.
Then you're super interested in all the age models?
I could talk about age models all day and debate about age models.
So why did you not use Cobra?
Because that's optimized for stalagmites, but you try and put a discontinuous lake sediment model with uncertain radiocarbon dates, because radiocarbon.
Sometimes you have 2 dates, right?
Sometimes you have 2 dates, and the probability distribution of possible ages looks like this for every single date. So thankfully Bacon, it's actually set up to have that, to incorporate that probability distribution, that bizarre probability distribution for radiocarbon, whereas the speleothem age models, it's made sort of your traditional distribution for the uranium thorium dates.
One question is, so you mentioned actually all of the data that you showed, the EOFs were derived from 8 data sets, right? The
8 sites.
8 sites.
And then some of those sites had multiple data sets within them.
But then what you show, you have this figure with the 8 panels of the 8 sites. But it seems like only one of those sites you actually have an increase or rather a decrease or actually an increase over the ice age. So if you cross-validate, meaning that you just remove the site,
I have.
and then you redo the EOFs, do you still get the same result?
I do. It's surprisingly consistent.
It would be site sensitive.
Where's my
So
bootstrapping?
the cross-validation here would be. So this is cross-validation.
Yes.
Interesting. Okay.
So generally the age uncertainties increase, but there's consistency. Yeah, I mean, none of the
Looks reasonable.
in the first EOF,
except for losing that one.
And that's Lake Kilimbeet, so that's the site with the most robust age model.
So that's one, and then the second is what was the name of the tool that you mentioned that you used for the age model?
Bacon.
Bacon, BACON?
Yes.
I
So
have a colleague
Bayesian accumulation histories, I think is what it stands for. It's created by Martin Blau, and it's available as an R package now.
Okay, I have a colleague that might be interested. I'll just write it down. And thirdly, you haven't really discussed global modes. That, for example, interhemispheric temperature difference or shifts in the habitat in the sense that in southern Australia, what you mentioned was that the precipitation there would be influenced by storm tracks, by what you call the Westerly belt. The latitude, the mean latitude of the storm track is affected or it correlates with the extent of the Hadley circulation. So to the extent that you have these global effects on either north versus south shifts of the Hadley cell, so that could be something interesting to look at. And then the effect of temperature here would be the expansion or contraction of the Hadley cell as well as and with it the Westerly belt. So it's something that you haven't mentioned that would be interesting. It might be relevant, for example.
That seems to be the next sort of exciting topic that, especially the scientists at the Bureau of Meteorology, they think that the subtropical ridge, the location and the intensity is going to be a really strong indicator of continental-wide patterns. But unfortunately, we don't have the data sets, we don't have reconstructions to be able to compare.
You don't have reconstructions of interhemispheric temperature differences and global mean temperatures. That would be the first thing to look at with regards to Hadley cell extent. I'm sure that there are.
I'm going to add it to my notes.
So that would be the zeroth order assumption, just how the Hadley cell is affected by global mean temperature and interhemispheric temperature differences, and if that explains what you see, then the more it's not really local, but say basin-specific processes. It's much harder to demonstrate, causality with these regional more low basin, say, average processes than with these large, more discrete. Yeah, but you haven't mentioned it, so that's what I'm asking. Yeah.
I think it would be interesting to be able to look at the larger picture hemispheric, but I'm not sure how strong of an indicator it would be of, if it's what percentage of the variability would actually.
I wouldn't know. You'd have to look at it, but because the southern hemisphere, especially in these regions, is more zonally homogeneous. I wouldn't say that about the northern. If you were talking about some caves in Asia, that would not be the same as talking about the southern tip of Australia, which is affected by a really zonally homogeneous belt. And because it's so zonally homogeneous, it is affected. So the arguments about, say, Hadley circulation type argumentation, that would actually be relevant in these parts, whereas it wouldn't be, just the other hemisphere.
We're lucky that we're mostly water in the southern hemisphere.
So that's what I'm saying. Otherwise,
everything out.
Which again goes to the point of these would be the first things to look at, I think. The effect of, so for example, the Hadley cell expands with the increase in global temperature, and that would give you the drier, I think, conditions.
So we push that belt of high pressure further south.
Yeah, so you would have the descent. So the descending range would be more over. So the storm tracks would be shifted poleward.
Even further south.
Yeah, and the desert part would be extended more towards the southern tip of Australia, I believe. And
I think that's what we've actually seen in recent decades, because the southern annular mode is becoming more positive, so we are seeing that shift.
Yeah, so the so-called desertation that we see in some places is associated with the expansion of the Hadley cell. So that would be one obvious thing to look at. And then interhemispheric differences in temperature also affect the zonal wind circulation, and not in a very simple way, but that would also be something very simple to look at. And if that correlates